Thanks everyone for coming. So I'm going to continue talking about something I was talking about on the last lecture, which is the Hugheskin monotonicity formula and how you can use this for singularity analysis. Okay, so just a reminder. So on Rn plus 1 cross negative time, we consider the function phi, which is a sort of modification of the backwards heat kernel, to be okay, so if this power here was n plus 1, this would be exactly the backwards heat kernel, but we're adapting the dimension to the dimension of our flow. And similarly, we want to change where the point becomes singular, so we allow the singularity of the heat kernel to form at this arbitrary space-time point. So this is just a space-time translation of heat kernel. Okay, and so then what we had was this Hugheskin monotonicity. Right, so this said that if we had a mean curvature flow defined by the interval 0 to t, then the change of the integral over sigma t of okay, so it's the, which of course is non-negative, sorry, non-positive. Okay, and here, of course, we're assuming implicitly that t is less than t0 for everything to be defined. So we see that if we, as we vary this weighted volume, where we have this sort of Gaussian weight that varies in time, that decreases, and in fact it strictly decreases unless this identically vanishes, which, as I said last time, if this quantity identically vanishes, that corresponds, say, when the x0 and t0 is the space-time origin, to having a flow that's parabolically self-similar about the origin. So that would be a so-called self-shrinking flow. Okay, so that's our basic tool that we're going to use to study the mean curvature flow, especially its singularities. And one of the consequences, as we of this, is the so-called so an important consequence for any t naught inside of 0 to t. Well, we need the time t naught to be before the initial time, after the initial time, but we allow it to exist up to the time where the flow ceases to be smooth, so we include capital T. We can define the so-called Gaussian density of the flow. This is the so-called so this is going to be defined to be the limit as t increases to t naught of the basically this quantity, so the integral over sigma t of right. And the point is, this quantity is decreasing, so this limit is always well defined and is finite, at least for as always. We're assuming our sigma is reasonable enough that this number is finite. So this is always exists, and it should belong to possibly 0, but it's definitely not infinite. Okay, and just to understand what this density looks like, if our flow, the flow is, say, the flow of a shrinking sphere, again, let's suppose, I mean, of course, the 0 to t is not strictly necessary. Then we can see that we have basically the density of x naught t naught, or here we assume t naught is, say, less than or equal to 0, has 3 possible values. So it's 0 if t naught is less than or equal to 0, and well, let's just say it's less than 0, and x naught does not belong to, let's call this sigma t. So if we're not on the flow, we can check that this guy gets localized closer and closer to the point x naught t naught as you approach t naught. So if you're away from the flow, you're not seeing anything when you take the integral. So you get 0 when you're not on the flow. Similarly, the normalization is chosen so that when you're on the flow, right, again, this is getting localized closer and closer to this point, but because you're at the flow and you're at a negative time, so you're away from the singularity, sort of as you zoom in, which is what this is doing since it's localizing, and it's scale invariant, which I mentioned, you're going to get something that looks closer and closer to the integral of this guy over the hyperplane, which the normalization n here was chosen precisely so that integral gives you 1. So the density of a sort of regular point is 1, and then the sort of interesting value is that you get a specific number, lambda n, which is strictly bigger than 1 and has an explicit value, which I don't want to write down. This is when t0 is equal to 0 and x0. Right, so at the singular point, the density is strictly bigger than 1. So in other words, this density detects the singular points by the points where the density is positive. I mean, bigger than 1. Okay, and another remark is, I mean, you might notice from this definition, and of course it's 0 if you're at t0 is equal to 0 and away from the origin. So this function, it turns out, is clearly not continuous in x naught and t naught, but you can check that it's upper semi-continuous, so it's allowed to jump up, but it can't jump down. So that's another consequence of the monotonicity formula. Okay, so that's the density, and what the density is going to allow us to do is I want to make this idea that if you zoom in, say, near a regular point, you get 1 because you look flatter and flatter. We're going to use that and see that you can make this to make sense of the fact that if you zoom in even at singular points, you get the mother model, which is a self-shrinker for any flow. So this is the notion of the tangent flow. And this is, if you're familiar with the theory of minimal surfaces, you know there's this concept called the tangent cone of a minimal surface, which says that at a singularity of a minimal surface, you rescale, you should get a minimal cone. This is the parabolic analog of that. So how does this work? So again, let's consider our mean curvature flow. And let's fix a fix a space-time point x naught, t naught with t naught, again, positive time, and we allow it to go up to the time where the sigma becomes singular. And the idea is, like, suppose that this following limit exists. So let's suppose this guy has a space-time track, script s. So suppose we could zoom in around this point x naught t naught and dilate the flow parabolically. Remember, we have this dilation invariant symmetry of the space-time track. So suppose the limit, I'm going to write this in this way. So it's right. So this just means translate in space-time the space-time track so that this point is the origin, and then dilate parabolically in the way I said. So zoom in. So suppose that this limit converged in some sense. So this is in some sense, which I will depend on. I'll say a little bit more in a bit. So suppose this converges in some set to some g, which we now think of as the space-time track. This g is now the space-time track of some new flow. Right. So in other words, it's each time slice should be a hypersurface or some kind of generalization of hypersurface, gamma t, where here t belongs to some interval I. And the point is, because we're zooming in, this interval is getting bigger and bigger. So the point is, we have two cases. So I is either the full interval if t naught is strictly less than t, or it's like maybe this half interval. Okay. All right. And the point is, if this convergence is reasonable, say locally smooth, then this new limit is still a mean curvature flow, right? So this is a and the point is, again, because of the dilation invariance of the Gaussian density, which I mentioned, we can see that if we do this dilation, we're not really changing the value of this weighted integral on the gamma t's. And the point is, since we're getting close, if we're a fixed distance before 0 on this flow, that corresponds on this flow to becoming closer and closer to t0. So if we compute this, how this works, and the fact that it's dilation invariant, we are able to work it out. So we can check, once you go back through the definitions, that in fact the integral over gamma t for any t less than 0 of the density, and here it's now centered, I'll just write it out to be clear, it's centered at the origin, right, because we've moved everything to the origin of phi. This is actually this Gaussian density at the x naught, t naught, of the original flow. This is okay. So in other words, this guy is constant, right? Notice this is independent of t. Right, so this implies that, of course, as we said, that if you have have constant in the Huysken monotonicity formula, right, because this is a mean curvature flow, then you have to be self-similar. So this implies that gamma t is at least backwardly self-similar. Right, notice, I mean, this is not really relevant for the discussion I'm doing now, but it does become relevant. Notice we don't actually say anything about forward time, so we don't know that it's self-similar in forward time. We don't have a monotonicity formula that tells us that at present. Okay, so it's backwardly self-similar, in particular that implies that gamma minus is a self-shrinker. Okay. Okay, so we would call this this flow um, gamma t for t less than 0, we call this flow a the in this case. Okay. And I think in my understanding, the Chinese language, there's no distinction between the and so it's important that this is, because we're making this strong assumption about the uniqueness of this limit existing, then this is the only possible limit. So what this tells us is that if we can take this limit, then we would get a model that is exactly a self-shrinker, which is the intuition we have. Now the problem is that this is a very strong hypothesis, and not one that one can, there's no reason a priori that this should be true. However, as is often the case in sort of geometric problems or geometric analysis, so this is sort of too strong, too good to be true. What I mean is a star. So what often happens is instead that there exists, say, you can assert that there is, say, for any sequence, a subsequence, so that this limit converges. So you can usually, the point is there's usually some compactness theory. So what's more believable is that there exists, you can take a sequence going to infinity. And so then in this case, the limit of the sequence of rho I well, this now depends on the sequence. Right. So, and the point is, again, maybe I give you a sequence, this limit doesn't exist, but it's a compactness result, so maybe there's a subsequence, so it would exist. So in this case, this would be in this case, we talk about a tangent flow. Okay, but the same analysis works. So any of these, if this limit exists, then it should be backwardly self-similar and be a self-shrinker. The point is it may be a different self-shrinker if you choose a different sequence. So that certainly conceivably could happen, though it's a question of whether it does. Okay, so that being said, in what sense do I mean taking this limit? Right. So right here I might say up to some sequence. Okay, so when is it what allows me to pass to a subsequence? So here I would, so when can I, this can be one. Okay, so the point is you're going to need some kind of compactness theorem to do this. And one thing you could do, for instance, is to assume that if you work this out, the limit, and this is a traditional way to do that, the limit, or let me say it this way, for t less than t naught, if the sup over sigma t of t minus t naught times the second fundamental form of sigma t, if this is uniformly bounded by some finite constant, right? So in other words, if the second fundamental form, it's allowed to blow up as you go to t0, but not allowed to blow up too rapidly. It turns out that if you do a parabolic dilation, sorry, there should be a squared here. If you do a parabolic dilation around t0, then this stays uniformly bounded. This is scale invariant. And so then when you take this rescaling, the curvatures of the flows are all uniformly bounded. So that means, as we go back to the first thing I mentioned, when you have a bound on the second fundamental form, you get a uniform scale. You can write it as a graph with uniform bounds on the gradient and the Hessian. And so then you can appeal to sort of Arzela-Ascoli. So then there's a kind of Arzela-Ascoli theorem and some kind of regularity theory, which implies some kind of C-infinite Moch convergence. Okay, so this is if you know some kind of curvature growth assumption, then you can blow up and you can get that the limit actually converges in some nice smooth topology. So what that means is locally as graphs. Okay, so this is, of course, there's a lot of thought about how this goes. Of course, there's no real reason this can be. I mean, it's very hard to establish this generically. What the more interesting way is to look at a kind of weak convergence and measure. So in other words, in measure. Right, so there's this sort of weak notion of mean curvature flow where you think of it not as surfaces evolving, but sort of measures evolving, where the measures are the surface measure of the mean curvature flow, and using the first variation formula. So in that case, you can always pass to a limit because you have sort of local mass bounds that are dilation invariant, and then you can get a limit that's some kind of measure theoretic self-shrinking solution. So this, yeah.
If T0 is less than capital T, is this, do you get an interesting limit?
No, so in that, I mean, since we're assuming it's already smooth, if T0 is less than capital T, you're just going to get the static plane. But I figure, I mean, you might imagine, again, once you have a weak notion of solution, you might allow a weak flow, and then it would, of course, be interesting. But yeah, so the interesting examples are always going to be when you're at the singular time.
So basically, if it's type 1, then T0 is equal to capital T, and this canyon flow is always like self-shrinker.
Well, it's always a self-shrinker, but it's actually like smoothly converging to the self-shrinker, and the self-shrinker should be smooth with curvature bounds. So that's true. The point is, there's no reason to believe that this is true for, I mean, this is hard to establish. Whereas if we allow this weak convergence, we'll always get a limit as a weak object. So we'll always get some kind of, weak limit. So this gives a sort of weak limit that one can then try and analyze. So this, of course, requires getting into geometric measure theory. So this is a very powerful, important way of thinking about things, but obviously sort of beyond the scope of what I want to talk about. So we'll maybe take this for granted that we can take some kind of limit. So one of the issues, as I'll allude to, is, what can go wrong in this weak formulation? And maybe I'll mention some conjectures and some results. Yeah, so maybe I'll just say this as a remark. Of course, it's if T naught is less than T, then of course our curvature is uniformly bounded, so we're always in this dagger is true. This dagger is true. And in fact, in this case, the tangent flow there's only one tangent flow, and the tangent flow is a static plane. Right, so we're really only interested when we're at the end time where a singularity forms. Okay, and so then let me just remark. So again, there's this issue in the second case. So if you have actually if you're actually looking at something like this, so double dagger, you can really get. I mean, there's two issues. So there's the sort of issue. So it's like the limit may be quite singular. And then the other problem is that the convergence, right, may be singular. So So there may be some regularity for the limit, in a way I'll mention, but even if that's true, the convergence of your flow to that limit may be singular. So you're not able to read off the information from the limit to the flow that you would like. So let me just make some known results along this line and a very important conjecture. So again, I'm maybe being a little vague. So there's an important theorem due to Ullmanen, which is unpublished, but you can find on his website. So he said that when the ambient dimension is 3, and some additional assumption, so maybe like, and the sigma t, say closed. So we're looking now at a smooth smooth flow, and we're looking at the first singular time. Then any tangent flow at t not equal to t has smooth support. Okay, so the idea is if you rescale and look at the limit will be a smooth self-shrinker as a set. But the point is, as a measure, it may have higher multiplicities. So the point is, it may have multiplicity, which is to say that the limit is not a smooth is not smooth because it has density 2, say. And the point is, in this case, even though this part somehow the limit is smooth, the convergence won't be smooth because you may have little necks that are kind of causing bad behavior. Okay, so but at least when your dimension is 2, the rescaling gives you a nice smooth limit as a set, but not necessarily as a measure. So once you know this, there's a very important conjecture again. So this is probably the most important conjecture in the subject. This is a so-called multiplicity 2 conjecture, or sorry, multiplicity 1 conjecture. Okay, so this says basically that the tangent flow, and again, let's think about the n equal 2 case. The tangent flow is actually smooth. I.e., the multiplicity of the measure is 1. Right, so the idea is, again, the picture is sort of what Ullmanen is saying could happen is you rescaled, your limit might be, say, a shrinking sphere, but the flow might look like, this might be what you look like very close to it. So it's very close. I mean, it's converging to the sphere, but it's converging with density 2. And the point is that the convergence here, the second fundamental form here is blowing up in the limit. But the conjecture is that doesn't happen. So at least at this first singular time. So this is maybe the big open problem. Okay, so that's this notion of taking a tangent flow. Now let me make one final remark about this question of whether we're taking subsequence versus the true sequence. So this is again a very interesting problem, and as far as I know, in the case of mean curvature flow, there's actually no example where if you have this and you can't do this. So Brian White has some related problem for like harmonic maps with a certain type of metric that's not real analytic, where you really do have to treat this. But in the mean curvature flow, this is not known to happen. And in fact, there's work of Felix Schulze, which says that if the singularity model is a compact shrinker, a closed shrinker, and you have this multiplicity 1 result, so if it actually, the singularity model is a closed self-shrinker with multiplicity 1, then it's the unique one. So then you're in this case. So that's what uses the so-called Voyasevich inequality adapted to the problem from Leon Simon. So in a much harder result, which is due to Colding and Minicozzi, they show the same result, again under a kind of multiplicity assumption when the singularity model is a shrinking cylinder. So that's much harder because that's a non-compact model, which there's not a lot of theory on. And
the X cannot deteriorate.
so in other words, they basically proved that if you get it one cylinder, it's the only, I mean, you can't change, and it's really the only object that can arise. So that's a... Okay, so that's... and so there's questions, of course, along this. I mean, maybe could you... I mean, is it true in other... I mean, if it's not a cylinder but non-compact, or maybe... I mean, maybe you have to prove this conjecture to use this, but maybe you could drop this. I mean, there's certainly questions there, so not easy ones. So there aren't, as far as I know, certainly not in Euclidean space. I would guess you could maybe find an example in a Riemannian manifold with a smooth metric that's not real analytic. So there's examples to like harmonic maps where there's a very similar uniqueness question due to Brian White, where he constructs an example of a singular harmonic map into a smooth manifold, but the manifold is not real analytic, where there is non-uniqueness for the tangent harmonic map. So there definitely are examples where it's not unique in some geometric setting, but not, as far as I know, in the mean curvature flow. Yeah. Okay. Okay. So then, as I said, we know we see already in this example, and also in the in just this observation, that somehow at a regular point we expect the density to be 1. So at a singular point we sort of would hope that maybe the density has to be bigger than 1. So we certainly see that in this picture, but that's actually